Swayam Prabha. Digital India. Educated India.
Let's go through another important analytical tool for our kinematic analysis. So this is moving reference frames. This is in contrast to our usual fixed reference frames. So let us say this can be equally applied to 3D, very easy. So this is usually the frame which we talk about, and then let's say if there is a particle P which is denoted by R, and so this is with respect to R. We know that R is given by xi plus yj. I keep writing this one because very soon we are going to extend this one to another coordinate system too. Okay, so if the position vector R is given in this manner, xi plus yj, and if we want to find out the velocity, so it's very easy to find out. We have done that. So if you want to find out v dr by dt, so I'll put it x dot. So that means that the time derivatives of x and y, you put it, and then they are in the directions of ij. So if the x coordinate is changing with time, so you can find it and then put it in the same direction I, and find out the y dot and put it in j, and then vectorially you add it, so that will give you the velocity. Okay, so this is what we have been talking about all the time, but many times what happens is that there are many situations where in your say mechatronics and so on, so there are so many applications here, or even so there are so many things here. So there are situations like this one, some simple linkage or even some robo. So wherein you have one link followed by another link on which other, sorry, usually I keep it on silent. Okay, so if this is a particle P which is moving along this, while this OA is rotating, while this is rotating with respect to this one, and variable distance R2. So this is how, and a number of links if you want it. Okay, even the crane or even earth moving equipment and so on. So in which case what happens is that this can be done with respect to xy axis, but when it comes to this one, so this theta 2 is given as a function of time, and even r2 is given a function of time, while obviously it is rotating about this fixed axis. So sometimes it's even convenient that we have some reference axis which is fixed to this link. Okay, so that way the description of this kinematics of this linkage will become easier, but then it will, the complexity is now transferred to what will happen to this if you fix some coordinate system here to this link. So obviously it is moving with respect to this. So if this is a fixed frame, and then this is something here which is translating as well as rotating as well. So then that means that what will be the final velocity of this p with respect to the fixed coordinate system, that's what we want. And how is it related to how, when it can be measured with respect to what's going to be added as an extra terms. So there are a lot of correction terms that need to be brought in. So for that, we need to study this moving and moving frames. Okay, I hope you have understood. So yeah. Okay, so this is a fixed frame, and this frame is fixed to this link, and which is rotating as well as translating, while this p itself is moving with respect to that moving link. Okay, so these are all very important applications, and there are many applications of this kind in mechanical engineering. So this where certain things rotate as well as move, like in mechatronics. Okay, so let's try to understand it in a systematic manner. So to start with, if this is a fixed one, so this is what we know here. And so when we talk about moving, we mean that with respect to this one fixed frame, so there is okay. So this is now I put two frames. This is a fixed frame xy, and so there's another frame x prime y prime, which is having an origin, and so this frame itself is moving, and obviously with the origin. So this point is moving, and then the point P is measured with respect to the fixed frame, as well as it is measured with respect to this frame x prime y prime. So when we talk about this fixed frame, we say that it is along the line at an angle of theta. Okay, this is the radial thing. On the other hand, so maybe we have let me just make it here. Okay, along phi. So while it comes to this description of this particle P with respect to the x prime y prime axis, so we say that this point P is along a line which is at an angle of theta with respect to the x prime, and then maybe it is moving along this line, as well as that line itself is rotating. So this is to bring in another frame of reference. Okay, so this frame of reference can have two types of fundamental motions which combinedly give a general motion. One is the translation. So this moving x prime y frame has one translational obviously with respect to fixed frame. And also it may have rotational. So this moving frame can fundamentally have two types: the translational, rotational, and general, in the sense that so this expand O prime y prime may translate in the sense that the axis x prime y prime axis remain parallel while this frame is taking another position. While it is rotational in the sense that if you have x prime y prime and that is going to rotate. So rotation, we will see everything in detail, but so rotational in the sense that, so if this is the basic frame, so that means that this x prime O y prime, which is there at the same origin, so will be rotating, and it has certain angular velocity, angular acceleration as well. And that means that here, this point P here is observed in both fixed frame and the x prime y prime reference frames. So how they are related when you talk about velocities and acceleration. So this is what it is. So that's the rotational part, and this is the translational part. And general, so I'd introduce double primes and so on. So once you start understanding, we will drop all those signs. Let me just, maybe I think it's just. So what it is that this, so you're able to understand in the first case, in the translation thing. So it is just these axes remain parallel to original axis, and then they keep moving with certain velocity and acceleration. While rotational means at the same point, so this x prime y prime axis is going to have certain angular velocity as well as maybe some angular acceleration as well. So this P is now observed in x prime y prime, also in the fixed frame xy. Okay. While this is a general case wherein this whole thing is translating as well as rotating, both will be done simultaneously. But in any case, so that means that this is sum of these two motions. Okay, translational and rotational will be the general motion. So let's try to understand one by one. So this translation part is very simple. So here this P, which is observed in the fixed frame, so that means that we have R, which is necessary for us, is RO prime plus R prime. So this total position vector with respect to the fixed frame is a sum of R prime as well as the R prime, which is observed in x prime y prime. So if you want to now go to velocities, so this is a very simple one. So if you want dr by dt, then maybe just to be consistent, which will be useful for us, let me write. So this is xi. It's very important for us. And rho prime is nothing but x4 I. Okay. And r prime is xi. Okay. So this is how these things are measured together with the unit vectors. So now, if you want to take differentiation with time, so that we get relationship with velocities, so we have dr by dt. You can very well see that it's nothing but each one of them. So for example, I can write it dx4y by dt. This looks very trivial, but let me write it all the same. This is the first part, prime. I mean x4, right? And then r prime. So in which case I will write dx by dt I. Okay, so here I did not take the time derivative of I and j at this stage because in the translational thing, so if you want, I can even put primes here. Okay, if you want, I can put prime because they are in the prime coordinate system. So I need not take the time derivative of I prime and j prime. So di prime, for example, is 0 because I prime is the same as I, which is fixed. Which is, since original ij are fixed and I prime j prime continue to be parallel to ij, so they never have any time derivatives. So that way, so this is very important to understand how the time derivatives are related. So that's these two. Okay, so maybe I should repeat it here. So what I'm trying to do is that I'm trying to take the time derivatives of this relationship. So in which case I use this dr by dt. So on this side, so we have O prime, which is given as the time derivative of these quantities. So they are products. So then we have dx naught by dt I, dy naught by dt j. And similarly here we have let's say, dx prime by dt and dy prime by dt with j. And I need not take the time derivative of these I prime and j prime because I prime j prime are parallel to ij and they are fixed, ij are fixed. So there is no time derivatives for I and j. So that's what I wrote. Di prime by dt is 0 because I prime is the same as I, which is fixed. And continuing this one, so which says that I can even directly write v. So the velocity here as is nothing but velocity of O and velocity of v prime. Okay, so just to make sure that this is the observation in xy and this also in xy and this is in x prime y prime. So in fact x prime y prime is just parallel to xy, so it doesn't make much difference even if you drop it here. So essentially this is kind of your relative motion. So in the kind of relative motions which you study in your 10th class or 11th class, where the frames or the observations are made in different frames, but then you should have kept in mind the frames remain parallel to the original frame. So they are the same directional frames. Okay. So whereas now we are going to go into another very interesting rotational frames, which is of very important for us. Okay. So once you understand this one, so let's go to the rotational part, and then the general is nothing but this VO prime need to be added. That's all. Okay. Okay. Now let's try to understand this part. So in which case, let us try to explain again the XY rotational frames. So here this OP is now observed in both. So for example, if this is XY, while this is X prime, Y prime. Okay, I hope you can see now that this P is now observed in XY as well as X prime, Y prime axis. So, and then the origin is at the same point. So if this is so, then what is that which we can say here? R is observed as Xi plus Yj, right? As well as, if you call it as R prime, so it is also observed as X prime, prime, J prime. Okay, so this is the observation made in prime. Here, since the origin is same, so the position vector R as observed in XY and position vector R prime obviously are same. So now what we do here, if you want to get velocity, differentiating with time, so what we have here, dr by dt is nothing but velocity in the fixed frame. That's what we want ultimately. And while this is the one here, d dt, so I'll put it here of X prime, I prime, and the second one also I'm putting it here at the moment, and the, so it's X prime di prime by dt okay. So I hope first I took the time derivative of X prime I prime, and then I took this also dy prime by dt J prime, and then I took X prime di prime by dt Y prime dj prime by dt. So this takes care of all the 4 terms. Okay, so this is d dt of X prime. So I can write it as X prime dot prime and Y prime dot J prime. So what is this? I'll just ask you. I'll write the other one. So the first one in the bracket, whatever is there, is that it's a complete observation in the rotating frame itself, because X prime is observed in rotating frame, I prime is also the rotating frame. So that means that this in the bracket is completely in the rotating frame only. So the person sitting in the rotating frame as well as is rotating, then if he sees a point P and then how he observes it is this one in the bracket. Imagine that there is, in fact, P being here, imagine that there is a point P, maybe a bead, which is moving only along X prime axis. So the person sitting in X prime Y prime, he only keeps seeing that ant is moving along X prime axis only. So he doesn't know that the whole frame is also rotating actually. So if some ant is moving this way, but the rotating frame is there, but he doesn't know that it may have a rotational component. So he only sees that, okay, the ant is moving only along X prime axis. That's all. So that's what the one in the bracket. But to that, we also need to have some kind of, if you call it correction, but another term which takes care of rotational component. Okay. So what is this di prime by dt? So how do we do that? So if you look at this di prime by dt, so what is I prime? So this is I prime and this is j prime, and this is obviously di prime by dt is nothing but delta I by. So what is delta I prime here? So delta I prime is because here there's a theta and there's a delta theta here. In a small time, this X prime has moved through another part here, and then this is delta I prime. So I prime has moved through an angle of delta theta. So the change in I prime is nothing but this small arc or a small card. So we know that if it is in the limit, so its magnitude, we have done this earlier. So the magnitude of delta I prime is nothing but 1 times delta theta, and the direction delta I prime is nothing but what? So if this is j prime, so you know that in the limit, so this is nothing but parallel to j prime. So it is nothing but j prime. Okay. So if you now this delta I prime can be written as delta theta in the direction of j prime. Okay. And if you take a quotient with delta t, so it is nothing but di prime by dt is nothing but theta dot j. Right? Yeah. Okay. So a similar thing which we have done in the case of polar coordinates is essentially the same thing. So similarly here, if you have during the same time, if you have delta j prime here, so the delta j prime, you can see that its magnitude is 1 times delta theta, and then what else? Its direction is opposite to that of I. Okay. So we can see here delta j prime, the magnitude is delta theta, and the direction is minus I prime. So we can write this one as delta theta I prime with negative sign minus I prime, right? And by delta t. So what we have here, dj prime by dt is nothing but minus theta dot I. Okay, so this is the time derivative of the unit vectors because they are rotating. So this I prime, which is here because there's a theta change, so it's moving with a certain velocity. So d theta by dt is, they call it as theta dot, or you call it as a omega. So like that, so we have, so finally what we have here is that if I write that expression, so velocity is x dot I prime, y dot a prime, and then this is x prime di by dt is nothing but theta dot j, and y prime theta dot I. Okay, and interestingly, now we can nicely convert theta dot j. If you give an theta dot is an angular velocity, can be considered as a vector. So theta dot is an angular velocity if you call it as omega, and if you give theta dot as a direction omega k. So if theta dot is moving in a counterclockwise sense, then we can give its angular velocity vector as omega k. So if you use that, this part here, so will become and this can become as theta dot is omega, and j can be written as k times I omega cross I, and this minus I becomes omega cross j. Okay, so we can now write these are all primary coordinates here. So we can take omega cross out. Yeah, so this is the interesting part here. And so finally, the velocity is, so in a concise sense, so the first one in the bracket is the velocity completely, all these things, all these x dash, y dash, okay, I should do that, okay, and then the vectors, the unit vectors along which these x prime and y prime are measured along I prime and j prime, and together with another term here, omega cross x prime I and y prime j. So this now I can write it as v as, let me put it as, this is important. Yeah, so this is the important part. That means that the velocity of the particle, the one which we want it with respect to the fixed frame, is nothing but velocity as observed in the rotating frame together with a omega cross rxy. So this is just without any knowledge that you are rotating. So your observation just to say that your velocity as observed in the rotating frame without any knowledge that you are rotating. While this one is the correction kind of term, omega cross rxy, so that since it's rotating with respect to the fixed frame, so something beyond observation is there, and that is this one. Okay, so this is a very important relationship which we will use it in any day. Okay, so that means that the observation as made, the one which I'm telling. So if, for example, if there is an ant moving, say if there is a particle P, imagine that particle P is moving along X prime and there's an observer. So he only sees that the ant is moving only along X prime direction. So he thinks that it's just moving. But apart from that, you also know that the particle P is also having a perpendicular velocity component because of the rotation of the rotating frame. So which is missed in the rotating frame observer. Okay, so thus we have this relationship. This is true not only for velocities but for any vector. So true for any vector, say even A. So A can be observed in, say, in X prime, Y prime rotating frame, okay, or as well observed in the fixed frame. If there is a time rate of change of A, okay, as well as it is measured in the rotating frame, then I can write it as dA by dt with respect to the fixed frame is nothing but so this is what it is, right? So dA by dt, the time derivative in actually this fixed frame is nothing but as observed in the rotating frame, okay, plus together with a correction factor omega cross A, because this is the one which is missed in the, that is the difference between rotating frame and the fixed frame. Okay, so this is an important relationship which we are going to use. Now what I would like to do is that we can even generalize the whole thing. If you want to generalize it, it's very easy to generalize in the sense that if it is the general motion, so in which case
camera.
Yeah, sorry. Okay, so now what we have here, so this P is observed in two coordinates. P as observed in the fixed frame, while R prime is observed in the X prime, Y prime, which is translating with O prime as well as rotating also about this parallel axis. So this is nothing but your translation as well as the rotational part. So in this case, so for example, if you want to have the particle P, then what we need is the prime VO prime and VP prime here as observed in X prime, Y prime and omega cross. So this is the same thing as that, except that I added a velocity of the origin. So the velocity of the origin is coming to the picture because of translational, and this is the observation made. So together, this is if it is translational, and we also have another term here because of the rotational component. Okay, so this is an important relationship between how the observations, the time derivatives are related in fixed frames, and as well as how they are observed in the moving frames. So moving frame can have two components, translational and rotational part. Translational part is nothing very difficult, only this much. Only the rotational part, this is the one which many times gives you a lot of confusion. So let us try to understand. This is the velocity relationship. Let's go for the relationship of acceleration. Okay, so to start with, we have V here. So to do this one, now if we want to go to accelerations, so then we need d dt of, this is a fixed frame, right? So this is the absolute acceleration in the fixed frame. And now we have to do this one, d dt of v, and I'll continue here, d dt of omega cross or xy. Okay, so this is a very interesting thing here. And what is that here? So this velocity is observed in the moving frame, in the rotating frame. Okay, in the, this x prime y prime is nothing but the rotating frame. So to get its derivative into the fixed frame, so what is that which we need? What we need is the d dt of vxy itself. So that means that I want to get time derivative in the xy itself, right? So to do that, the observations are made in x prime y prime. So what we need? So that means that I need okay. And what else? I always need another correction term because the observations are made in the rotating frame. So now coming here, so d dt of the second one, first is omega. So d omega by dt, if you don't mind, I can write it as alpha itself. What is alpha? Alpha is d omega by dt, angular acceleration, times or xy. And what else? Omega cross d dt of rxy. So this is the interesting part here. I'll continue here. So this is dv prime and this is, they stay as it is, and this, the only term that is omega cross. So the time derivative of rxy. What is rxy? Rxy is a position vector measured in the rotating, this is prime, right? Yeah, these are all primes. because all these observations are made in the prime coordinate system. So this is omega cross d dt of, can I expand this one? So it's d dt of r x prime by prime plus here again omega cross. This is the interesting part. So again and again, you keep again and again. So when we want the d dt of this one, so that means that the time derivative in the rotating frame plus a omega cross rxy, which keeps coming as an extra correction term. So you can, we are almost done. I'll just collect all the terms, and if you collect all the terms, so it comes as, yeah, you have that. And if you collect all the terms, so what we have here is that acceleration as observed in x prime by prime. These are all x prime by prime, right? Yeah, okay. So there's omega cross vxy is occurring twice. So I will put it at the last. And we will spend time on this one. So I collected all the terms here. So all the terms here. So this is the acceleration of the particle as observed in the x prime y prime, while this alpha cross r is the tangential acceleration. You can recognize what this term is. This is the centripetal acceleration or normal acceleration while the particle is moving in a circular motion. So this is the one which is usually is not understandable. So 2 omega cross, I'm sorry, this is V. Yeah, this is the one, right? Vxy. Yes, this is B, because this is d dt of rxy. So this is the one which is known as Coriolis bonnet. Okay, so this has suddenly there are so many terms when you try to put a relationship between a fixed and a rotational frame of reference. Okay, so please go through it carefully, all the steps. So these are all very important to really understand the final relationship and apply it. Okay, I think I should stop here.